It's on.
Is it?
It's on now.
Oh, it is on? Okay, so we were talking about Goldstone's theorem last time, and maybe I should just, for completeness, summarize what it is. And it's basically, if you've got a Lagrange that looks like this, with a bunch of fields and some potential, then you expect that the potential at its minimum is whatever near its minimum is a sum of terms like that, and what we saw was that well, let's see, it might be easier just to prove the whole damn thing from scratch. Because of symmetry, the potential is independent of the parameters of the symmetry group, and so this is partial v partial phi j, partial theta r being one of the rth parameter. And so this is partial b, partial phi j, and the change in phi j is basically I, the rth generator, jk phi k 0, and phi k independent of whether we're at the minimum. And now if you take, so this is true for arbitrary values of the n vector of the field. If you then take a second derivative at the minimum, then what you get is partial phi j, partial phi k, or let me just follow my notes, partial phi l of I tr j k, say phi k, plus partial v, partial phi j I tr jk phi k 0. Right, so that's, I'm differentiating this with respect to, let us say, phi L, and now that I think about it, I should have erased, I should have followed the notes exactly. We're differentiating with respect to phi L, so this is the equation that holds for if we're at vacuum values. And at, well, no, this actually holds everywhere because it's the derivative of something that's identically zero. And now if we restrict ourselves to points that are minimum of the potential, the first derivative vanishes, and what we have is 0 is partial 2v, partial phi j, partial phi l, and I tr jk phi k 0. And the point is that these are the mass, this is the mass matrix m squared jl, and then this thing here is I tr jk phi k 0. That means that this thing is an eigenvector of the mass matrix with eigenvalue 0. So there are massless particles in the theory, at least apparently. And in fact, for every generator of the symmetry group, there is a vector that's an eigenvector of the mass matrix with eigenvalue 0. The only exception is when TR annihilates the minimum, this vector phi k0, in which case you have something that's identically 0, and eigenvectors can't be identically 0. They're actual vectors. They can have 0 eigenvalues or finite eigenvalues, but they can't themselves be 0. And so the rule is that each generator that does not map the minimum phi 0 to 0, or rather I should say to each generator that does not map the minimum to 0, there is a massless scalar. And these are called Goldstone bosons. Now, in reality, in the standard model, there isn't any exact massless scalar as far as we know. On the other hand, there are some light scale particles called pions, and various people have analyzed the strong interactions, taking the pions to be Goldstone bosons, and in fact Weinberg is one of the people who's done this, but I'm not going to go into that. So let's look at a couple of examples.
Can I ask you a quick question about the notation real quick?
Read that again?
Can I ask you a quick question about the
Yeah.
notation? Yeah, so you have some Lagrangian that's invariant under the action of some
Symmetry group,
that's described by some like Lie group.
Yeah.
And theta r are the parameters?
Theta r is a parameter, yeah, yeah.
Parameters
In other words, the group element G of theta, or let us say a representation of the group element near the identity is this plus I TR theta r.
Mm-hmm.
That's the idea.
Yeah. Okay. And so then the TRJK are matrix elements of your
TRJK are the matrix elements of the generators.
Yeah. Okay. Okay. Cool.
So let's look at a couple of examples. And the funny thing is that the examples that come to mind are, to some extent, misleading, although nature seems to have been kind to us and in the standard model, it's the simplest possible example, essentially. So let's look at SU2. Suppose the minimum vector phi 0 is just 1, 0. So this SU2 is acting on doublets, which are two complex numbers. So in general, phi is two complex numbers, and it's acted upon by a 2x2 unitary matrix of determinant 1. And now what you can see is that the generators of this don't annihilate this vector. Sigma 1 on phi 0 is 0, 1. Sigma 2 on phi 0 is 0i. Sigma 3 on phi 0 is just phi 0 itself. And so those don't annihilate it. So what we expect then is that for SU2, we have 4 both the real and the imaginary part of the two, each of the components is a real scalar field. So we have 4 real scalar fields, 3 Goldstone bosons, and 1 massive scalar boson, and so that's what, and well, it's massive, assuming that the potential is something like V of phi, in this case, is, say, phi dagger phi minus mu squared over lambda squared times, say, lambda. Something like that gives you, you would then have the minimum would be, it would actually be mu over square root of lambda would be the a minimum, but you could pick any minimum on a sphere of radius mu over root lambda sphere in four space dimensions. These fields, of course, were complex, and this analysis here was in terms of real fields, and in order to make the correspondence exact, one would look for fields. So we would have phi plus I, phi 2, phi 3 plus I, phi 4, and this is delta phi 1 plus I, delta phi 2, delta phi 3 plus I, delta phi 4. So one could ask, what are the 4x4 matrices that do this? And it turns out they are sigma 1 is 0, 0, minus 1, 1, minus 1, 1, with everything else being 0. Sigma 2 is 0, 0, 1, 0, 1, 0, and then down here 0, minus 1, 0, 0, minus 1. What you can see is that they're real and anti-symmetric, and that corresponds to the things being e to the theta dot sigma as being a 4x4 real representation of SU2. Sigma 3, it turns out, is 0, minus 1, 0, 0, 1, 0, 0, 0, and then 0, minus 1, 1, 0. So this is in a real representation of these correspond to I times the Pauli matrices. These are 4x4 real matrices that correspond to that. And the actual, now that I think about it, if this is the potential, then the symmetry group here is O4, and O4 has more generators than that. O4 is 4x4 real anti-symmetric matrices, so you have, you can fill in all, so there are actually 6 generators. Suppose we look at SU3, then the vector might be mu over square root of lambda. Again, one could set it to be 1, 0, 0. And now, if you recall the generators of SU3, there are 6 generators and 8 generators, and unfortunately I didn't print them out here. these generators are, I'll just call them T sub r, and 2 T sub r are what one might call lambda r. The lambdas are called they were originally called the Gelman matrices, but that was back in the 60s. I don't know if anybody except me calls them that at this point. In any event, we can you can then ask which of these matrices which of them annihilate this vacuum vector, and it turns out that the only 2 that do are T6 and T7 in the normal representation. By the way, these things are printed out in chapter on group theory. I write down all 8 of the generators. Actually, I write them out in terms of lambda because then you avoid over 1/2 everywhere. These T6, I just might mention, T6 actually is a half 0, 0, 0, 0, 0, 1, 0, 1, 0, and T7 is a half 0, 0, 0, 0, 0, minus I, 0, 0. These are the 2 vectors, 2 generators of SU3 that annihilate this vacuum vector. And so what one says then is that there are, at most, is the possibility of 6 of these real fields that are massless Goldstone bosons. But in fact, there are only 6, and one of them we know is massive. And the reason why there aren't 6 Goldstone bosons is that if you consider TR phi 0, these are the possible, for each of the 8 R's, 2 of them are identically 0 for R equals 6 and 7, and the other is that T3 phi 0 is equal to T8 phi 0, or at least they're linear. Yeah, in fact, I think they're exactly. They're certainly proportional. Did I write them down? Let's see. Yes, they're actually equal. So these 2 are actually equal. So these can't be linearly independent eigenvectors. So there are 5 Goldstone bosons. And 1 massive boson. Is that a question?
Yeah, I guess I was, I don't know, maybe I know what's going on now, but yeah, I was just going back to the case of SU2.
Yeah.
And you have your 3 generators, right? And
the Pauli matrices.
Yeah, and they don't map phi 0 to 0.
They don't annihilate phi 0,
yeah, they
right?
don't annihilate phi 0.
So we have the possibility of 3 Goldstone bosons.
Yeah, okay. So, I mean, yeah, I'm just wondering, like, is it always going to be the case that I'm going to have 1 more field than the number of generators that I have? But then I guess in the case of O2, you would have 4 generators? 3, 9.
Well, let's look at SU3. In SU3, we've got 6 real fields, 8 generators, and in this case, 2 of the generators annihilate the vacuum. In SU2, none did.
Yeah.
And in SU2, all the generator times the vacuum, those were 3 linearly independent vectors. Here, we have 6 vectors, but 2 are linearly dependent, so the 5 are linearly independent.
Sure.
So that's how it works. And if you want, you can do this same business, and in fact, in there are notes on spontaneous symmetry breaking and on the class webpage, and there I write out what the 6x6 in fact, the 8x8 matrices that correspond to here. Let's say that we have here phi 1 plus I phi 2 phi 3 plus I, phi 4, phi 5 plus I, phi 6. And we say that this is delta phi 1 plus I, delta phi 2, and so forth, delta phi 3 plus I, delta phi 4, delta phi 5 plus I, delta phi 6. What are the real matrices that act on these 6 real fields? And these are then 6 by 6 matrices, and lambda 1, it turns out, is, I'm not going to write them all down because they're 6 by 6 matrices, but this one looks like that. Whoops, wait a second, where am I here? This one is -1. Well, actually, it's confusing to write them down. It's 0. No, that is a 1. Let me get in the basic here. Okay, 0, 0, 0, -1, 1, 0. 0, -1, 0, 0, 1. Okay. And then all zeros here. So that's lambda 1. And notice again that they're real and anti-symmetric because they're generating a real 6-dimensional representation of SU3. And so the reason why I mention it in class is that we talk about, whenever anybody talks about group theory, the term representation is used a million times, and when in such lectures on group theory, though, it's almost always true that you only see 2 representations, the defining representation and the adjoint representation. So here, what I thought was a little bit interesting is that these sigmas are the generators in a real 4-dimensional representation of SU2. And over here, the 8 lambdas are the generators of a real 6-dimensional representation of SU3. And it's just a little bit interesting to see that. And what I'm wondering, what's running through my head is that now for just about the first time is that in both examples we see that the symmetry seems to be bigger than maybe they're the same size, but here we've got, we start out with SU2 and then we see, well, since this is the structure, this is just a sum of all the squares of the 4 real fields, so we really have symmetry under O4. And then over here, we've got symmetry under O6. And so the question is, isn't O6 bigger than SU3, and isn't O4 bigger than SU2? I think the answer in both cases is yes. So these are theories that, in which when we write them down, we think of a symmetry, but there's actually a bigger symmetry. Unless maybe I'm being silly. Maybe these groups are all the same. It just occurred to me now. I was thinking of it. Anyway, as you know, in the actual Higgs mechanism, what we have is a gauge invariant theory. And the idea with gauge invariance is that you have a unitary matrix acting on matter fields, and one makes this work by introducing gauge fields that transform this way. So this is then a non-Abelian gauge transformation that makes in fact, the real advantage of this is that di psi is then u of x, di psi of x, let us say, is u of x d psi of x. That's what this gauge transformation does for you, and so that means that you can write down, well, there's an I here. So you can write down fields like di psi dagger di psi, or fields like psi bar gamma a say, or gamma I if you want to, di psi, and under a non-Abelian transformation by u of x, there's a u here, a u dagger there, and they cancel, and so this is how that works. And then what happens is that Fij prime is u Fij u adjoint, and so you can have the trace of Fij prime. Fij prime is equal to the trace of Fij. And so your whole Lagrangian is something like minus a quarter trace Fij, and I guess it's, I forget what the overall sign is, I don't think I wrote it down here, but plus or minus I psi bar gamma a ta psi. So that's basically how one writes the gauge invariant theory. Now, what happens is that in the case of let us say scalar fields, in fact, let's do the very simplest thing, the Abelian Higgs mechanism. So let's say minus a quarter. So this is just going to be the Abelian case here. This would then be FAB minus dA, but a complex field phi. And then so this theory wouldn't. This would be a theory of a complex scalar field, a mass m interacting with the electromagnetic field, say, and there's not a great deal. Well, this is just the standard theory. There's no spontaneous symmetry breaking or anything. On the other hand, if we put a plus sign here, then there is spontaneous symmetry breaking. Let me say that phi here is 1 over root 2, phi 1 plus I, phi 2. And let us say dB phi is the Beef derivative plus I e AB on phi. And so when we have a plus sign, then we do have spontaneous symmetry breaking, and the minimum lies on a circle, and the circle is of radius m over square root lambda. And so the convention is to write the field phi as m over square root of lambda. In other words, everybody picks as the vacuum we like is the one where the real field assumes this mean value and the imaginary field is essentially 0. And so we write this as m over square root of lambda plus 1 over root 2, sigma 1 plus I sigma 2. And now sigma 1 and sigma 2 are real fields, and sigma 2 is just the original field phi 2, but sigma 1 differs from phi 1 by m over square root of lambda, apart from root 2. And there's another convention here, which is that this is sigma 1 plus I sigma 2. So what is really conventional is that V is the mean value, in, V over root 2 is the mean value in the vacuum. And that's because V is the real part of that field phi 1. Now, there's a lot of arithmetic, and I think I should basically skip it. It's in the notes here, and which of course are online. So if we write this as phi star phi plus lambda over 2 phi star phi squared, after a certain amount of cancellation, one gets m squared sigma 1 squared plus m squared of lambda over 2 sigma 1 times sigma 1 squared plus sigma 2 squared plus lambda over 8 sigma 1 squared plus sigma 2 squared squared minus m to the 4th over 2 lambda. So there's this theory is one in which there is some negative dark energy, if you want, but we could have written the theory differently from the beginning, and in fact, the way I wrote it over there, if you write the theory as phi squared minus m squared over lambda squared minus lambda over 2. If you take this to be the potential, then the mean value of the potential in the vacuum is just 0. And so there isn't any, you avoid this negative term here. So what this tells you is, apart from a constant, you have that the one massive field is sigma 1, and sigma 2 looks like a Goldstone boson. So it looks as though it's massless. But that's because we've only looked at this part of the theory. If we look at the covariant derivatives of the scalar field, then we find that things are quite different. And in particular, the kinetic part of the action, namely dA phi star dA phi, this, after a considerable amount of arithmetic, which I hope is correct, we get phi 0 squared. I did call that phi 0, didn't I? Here, phi 0 is m over square root of lambda. So this is e squared minus e squared phi 0 squared AA. So the electromagnetic field gets a mass in this theory, and then we have minus dA sigma star, dA sigma, and then some other terms, minus root 2 E squared AA phi 0 sigma 1 and minus square root of 2 E AA phi 0 dA sigma 2. Okay, so what's happened here then is that the gauge field has acquired a mass m, say m sub a, which is square root of 2 E phi 0. On the other hand, phi 0 itself is m over square root of lambda, so this is square root of 2 em over square root of lambda. And so this is the Abelian Higgs mechanism. What's happened here is that the scalar field is a complex scalar field. The real part of the scalar field assumes a mean value in the vacuum, phi 0. The fluctuations of the real part about phi 0 increase the potential, and so that corresponds to a mass squared term for the real part, for the fluctuations of the real part of the scalar boson. On the other hand, the imaginary part has fluctuations that are massless, so it would be a Goldstone boson, but it combines with the electromagnetic field to supply the third component of the massive photon. In other words, the photon in this theory is massive, and as you know, a massless photon has 2 modes, a massive photon has 3 modes. That third mode is contributed by the sigma 2. The easiest way to see this is, also the most physical way to see this, is to remember that this is actually a gauge theory. And so what one can do is one can do a gauge, whatever the field, for any field configuration of the electromagnetic field and the scalar field, the complex scalar field, one can do a gauge transformation at every point in space-time without changing the action. You do a gauge transformation that rotates the complex scalar field into a real field at every point in space-time. And when you do that, you find out that the Lagrangian is then minus a quarter FAB minus dA phi, because phi is the scalar field is just real, minus E squared phi squared AA plus M squared phi squared minus lambda over 2 phi to the 4th. Now, this is the simplest kind of theory. One then has spontaneous symmetry breaking of the single real field, and the vacuum then again is lambda, what is it? It's M, sorry. M over square root of lambda, and this phi then becomes phi 0. Maybe I shouldn't do it that way. I should just say L in the vacuum is then minus a quarter FAB minus dA phi, and then this thing is minus E squared phi 0 squared, which is m squared over lambda, AA, and then this is, well, if it's at the vacuum, it's just minus m to the 4th over 2 lambda. So in the vacuum state, what we have is this, and this is the, so this acquires a mass, and let's see, I left out something. This thing actually, yeah, I should have written it down more nicely. Right, I left out a term, damn it. Oh, here's the term right here. So, no, that's not the term. After symmetry breaking and in the vacuum, the extra term, so what do we have? This and that, and then we have minus a half dA sigma minus m squared sigma squared, and then higher order terms. So we have a massive scalar field where here phi is phi 0 plus sigma over root 2. So so in this, after making the gauge transformation, what we have is a massive vector field and a massive scalar field, and that's it. And then interactions that are cubic and quartic amongst the scalar field, the electromagnetic field, and self-interactions and so forth. This is called the unitary gauge. And so in the unitary gauge, what happens is you see more clearly what the fields are and this is called the Abelian Higgs mechanism. Okay, so now we should go to the non-Abelian Higgs mechanism. Unless there are questions. Are there any questions? All right, well, let me start with that. Then what we'll have is minus a half sum I equals 1 to n dA phi I dA phi I, and then we have m squared over 2 phi squared minus lambda over 4 phi squared squared. So the numbers are a little bit different, and that's because whereas over here we have one complex field, here we have n real fields. Scalar fields, phi I. And so if phi squared is just phi dot phi, then we have this usual business where you would say offhand that, in fact, let's see, yeah, all right. So let's just look at this theory from the Goldstone point of view, apply Goldstone's theorem to this case. So we could take as the vacuum vector something proportional to 1, 0, 0, 0, where this is an n vector, and So then we would say for each generator that does not annihilate this vector may be a Goldstone boson. And now, what's the symmetry group? Well, the symmetry group is ON. And so ON, the generators of ON, if we forget about this I business that makes everything more complicated, we make this theta R TR, and so these are orthogonal matrices. The T's then are real and anti-symmetric, and the thetas are real. How many generators do we have? Well, what we have here is that the generators have to be 0 on the main diagonal, and so for every row and column, you can put a 1 here, and then you have to put a -1 over there. So you have, for each of these, you have a generator. You set all of them equal to 0 except for 1. One of them you make 1, and then you have to put a -1 down here, and that gives you one of the generators. And so now, how many generators will not annihilate this vector? Well, it's obvious that this is an n by n matrix. This guy.
Should you have another generator too?
Excuse me?
Oh, sorry. Should you have an extra generator too, because the fact that we're working with ON and not SON, so these guys don't necessarily have to be traced.
Okay, all right. Let's think about that.
Well, I guess, how would you get a reflection of this?
Yeah, I haven't thought about that recently. I want an orthogonal matrix. In the case of SU and UN, the extra generator just has 1s on the main diagonal. But here, if you put 1s on the main diagonal, you're going to get something that's not orthogonal. These things, huh?
Or sorry, so we were just going to say, I'm wondering, like, how would you get determinant -1 anyways? Because if you take the determinant of that, that's equal to e to the trace.
Right.
Of the thing.
And the trace is
E
0.
to anything is never negative.
Right.
See, so how would you ever get a determinant? So I guess you need something else outside, like just some arbitrary reflection matrix or something like that? Does that count as a generator? I don't know. It's sort of...
Yeah, now, all right, let's think in the very simplest case. Let's say O3.
That way too.
So, yeah, O3, the deal is just reflections, right, and those reflections, you're right, they just have -1s on the main diagonal.
No, but do you see what I'm saying? So, that wouldn't be like a generator that we put in the exponential.
Yeah, it wouldn't.
Yeah, that would just be like something else that you put outside, like some reflection matrix.
In fact, I think that the actual, you really want, all right, let me.
Okay.
But a good observation. Now that I think about it, if I'm not mistaken, when Cartan analyzed all of the, I think it was Cartan, all of the Lie groups, he did SO2n, SO2n plus 1, UN, and SP2n or SPN, I forget which. And so ON is a little odd for the reason you mentioned. All right, anyway, to get back to this, what we've got then are n-1 generators that do not annihilate this, because you can have a -1 here, or you can have a -1 there. There are n-1 places. So there are at most n-1 Goldstone bosons, massless Goldstone bosons, and one massive scalar. So that works out very nicely. And that's because, and it works out very simply because we started with the group that is the natural group of the symmetry, whereas over there we started out with we had something that really was an SON, was an SO4 or an SO6, and we said no, we want to think in terms of SU2 and SU3. Anyway, so that's the way this is. But if we then add a gauge field, then what we've got is the non-Abelian Higgs mechanism, and so what we'll have here is a quarter trace of FIK, minus a half dA phi transpose dA phi plus a half m squared phi squared minus lambda over 4 phi squared, where phi squared of course is phi dot phi. And here what's done conventionally is one says that phi is pi 1 up to pi, say, n minus 1, comma, phi 0 plus sigma. And phi 0 is then the mean value. This is the field that becomes massive. These are n minus 1 Goldstone, massless Goldstone bosons. But when we put in the gauge field, things change, and these n-1 fields can make some of the gauge fields massive. And so let's look at what the mass terms for the gauge bosons comes from this term, which is the kinetic action of the scalar field. And the relevant term here is minus a half dA phi transpose dA phi, and so this is minus a half, and this is a sum IKL equals 1 to n delta IK dA plus a sum over all the generators 1 to n minus 1 over 2 IE TRIK AFA phi k, and then delta IL dA plus sum G equals 1 to n minus 1 over 2 IETG IL AG A phi L. So the phi's are all 0 except for one of them, and so what happens is this boils down, apart from the derivatives, it boils down to the kinetic part 0 is a half e squared phi 0 squared, and then it's TF IN TG IN AFA AGA, and the mass matrix then is M squared FG is E squared phi 0 squared I put the i's back in, I TF IN I TG IN. And with the i's in there, they actually are real, and I have here symmetric, but they should, oh, the m squared is real, so the m squared, of course, is real and symmetric. And so now, if we diagonalize this, it obviously can be diagonalized. We get the n gauge bosons that are massive and that are eigenstates of this matrix. And one can arrange then that m squared fg is equal to e squared phi 0 squared times delta fg k over 2, where k is the that constant that comes out of trace tr ts is delta rs, and there's a k somewhere, I forget where the k goes, so I'll write this as k to the plus or minus 1. I forget where the k goes. But you remember that when you define the generators of a Lie group, you want the structure constants to be the same for all representations. And so you have to scale the generators by a k in each representation. So we make the mass of these gauge bosons then is E phi 0, and what we have then is n of them is massive, n of them are massive, but on the other hand, the number of gauge bosons for SON is higher than n, because it is n minus 1, n minus 2 over 2. That's the number of generators. That's the number of gauge bosons in SON. This is n across, so this is 1 plus 2 plus 3 up to n minus 1, and that gives us this. And clearly for large n, that increases as n squared, whereas the number that get a mass is only increases as n, because they're the diagonal elements of this n by n matrix. And so consequently, it in the standard model, as we'll see, it works out very neatly that with SU2 cross U1, you have one massless gauge boson, which is the photon, and 3 massive gauge bosons. In the general ON case, you have, let's see, I think I wrote this down here. You have, well, first of all, you have a lot of scalar fields that remain massless. Let me see, all right, here. So you have n scalar fields, n minus 1 of them combined with n minus 1 gauge bosons to give you n minus 1 massive gauge bosons. One scalar field is massive, and then what you have then is not all, this is the number of gauge bosons, but the number, so let's see, maybe I made a mistake here because I just said that there was n of them were massive, but only got n minus 1 of these scalar fields that can make them massive. So let's see, I don't have the numerology perhaps worked out exactly. In any event, some of the gauge bosons are massive, at least n minus 1 of them, possibly n. One of the scalar fields is massive, and many of the gauge fields remain massless. So it's a mixed picture. So let's now go to the standard model and the actual Higgs mechanism that seems to be realized in nature. I'm looking here. So I guess I'll have to erase something. So as you know, in this case, the gauge group is a funny group. There's a U1 that's called U1 of hypercharge, and then there's an SU2, and the SU2 is weird because it acts only on the left-handed spin 1/2 particle, or left-handed spin 1/2 fields. Remember, a Dirac field is a 4-component field in which 2 components transform according to one representation of the Lorentz group, and the other 2 components transform according to the other representation of the Lorentz group. And these representations are such that the rotation subgroup of the Lorentz group is represented the same way in both representations of the Lorentz group, but the boosts are represented in opposite ways with basically a minus sign. So what we have is a scalar doublet. I didn't need those parentheses, that's for sure. 1/4k. K is that constant that scales the generators. Trace FAB plus m squared phi squared minus lambda 5 to the 4th. And 5 to the 4th here really means absolute value phi squared. The gauge field, the vector gauge field is IE ½ times the Pauli matrices. All right, so first I'm going to do the SU2 Higgs mechanism, and then get to the standard model. So for just SU2, the gauge fields look like this. This is the Pauli matrix, and these are 3, well, actually, I'm sorry, this thing is A sub B, and this is a dot product of generators dotted into gauge fields. These, of course, sigmas are the Pauli, regular Pauli matrices. And so dB of phi, the ith component is dB phi I plus IE ½ sigma k ij AB k, because the k goes with the sigma, and then the phi j. And this, of course, is invariant under gauge transformations where phi prime of x is either minus I theta of x dotted into sigma over 2 phi of x and A prime b of x is, well, e to the minus I theta dot sigma over 2 AB e to the I theta dot sigma over 2 plus I dB e to the minus I theta dot sigma over 2 e to the I theta dot sigma over 2. So that's the gauge transformation. And here, of course, trace of a half sigma I, a half sigma j is a half delta ij, and so the physical way to understand this is to go to unitary gauge again. And the unitary gauge we can take is 0 b plus sigma. And now that I think about it, this ought to be over root 2. But, all right, let me stay with, let me follow my notes directly without trying to change the notation. So phi 0, here is 0b, and here b is m squared of 2 over lambda, square root of 2 over lambda. And so the kinetic action that gives rise to the masses of the gauge fields is then IE 1/2 sigma k ij AKB phi j dagger IE 1/2 sigma m IL AM B phi L, and in matrix notation that's E squared over 4 phi 0 dagger sigma k sigma m phi 0 AKB AMB, and there is, of course, this standard relation for the Pauli matrices. Sigma k, sigma m is delta km plus I epsilon km L sigma L. And so, for example, sigma 1 squared is just the identity. And if you plug that into here, what you get is 1/2 m squared ABK ABK. And so here then all three gauge bosons get mass m equal to EV over square root of 2. And so this makes perfect sense here because we started out with 4 real fields, and we can use 3 of them to make the 3 gauge bosons massive, and then 1 is left over that is massive. And so that's a case where this spontaneous symmetry breaking in the Higgs mechanism is very, very neat numerically, whereas in the case of SON, one has various gauge bosons left massless. and some made massive. So one can put the Higgs in the adjoint representation. That would give us a different picture. I don't know how useful that is to go through in class, so maybe I'll just summarize it. In the actual Higgs mechanism of the standard model, what one has is an extra symmetry, an extra U1. Maybe I'll talk about that for a few minutes since we're almost out of time. The extra U1 is an e to the I theta times will be a gauge field, or, I mean, will be a generator, and the generator in this case is called Y, or hypercharge. And so this is the U1, and then one has the same SU2 that we've been talking about here. So the general picture then is one has one extra gauge field for this that gauges this U1, and we call that B, and we can call these, let's see, I didn't print out this part of my notes, so I forget what I call them, but we could just call them as the three vectors A. So you start with 4 gauge fields, and what we'll see on Wednesday is that if we then look at the kinetic part of the action of the scalar fields, we'll have one linear combination of B, and one of the 3 gauge fields will remain massless, and the other 2 of these will become massive, and then an orthogonal linear combination of B with A will become massive. So it's in fact the B plus A3 linear combinations, not exactly this, but well, alpha plus beta, that will be 2 different linear combinations. One will be massive, one massless. Massless one, of course, is the photon. All right, so we'll do that.